The intention of today's video is to provide you with a few more tools that you can keep in your toolbox that will hopefully allow you to balance some of the more difficult equations. Up until now, we have discussed a means through which we can show our work while we're balancing our chemical equations, which we will use to solve a few of these problems. And also we've discussed the theoretical basis as to why we must balance chemical equations. Again, just as a quick recap, the reason that we must balance a chemical equation is because a chemical equation is a representation of a real-life chemical reaction. And since chemical reactions are governed by the law of conservation of mass, we must, in our chemical equations that are representing these chemical reactions, also satisfy the law of conservation of mass. And in order to make certain that we do this, we need to check to make sure that the amount of atoms of each respective element is present in both the reactants and the products of our chemical equation. Since we cannot change the compounds that we are working with, that means that we are unable to change the ratio in which the elements exist in the compounds themselves, that we must instead change the ratios in which these compounds interact with each other. Because again, these chemical equations represent real-life chemical reactions, and by changing the subscripts within the molecules in the reaction, we are changing the substances that we are representing, and we may no longer be representing the chemical reaction that we are interested in. Now, these are intended to help with some of the more difficult chemical equations where we have more elements present than just the few that we've worked with to this point. As we go through these, we will increase the difficulty of the types of problems that we will see. So for example, our first tip and trick is when we recognize that there is a polyatomic ion that is present on both the left and the right of the arrow, it is best to keep that as a unit and balance the polyatomic ion as a unit. I recommend that all Chem 1 students memorize these as early in their career as possible so that they are able to identify and recognize these polyatomic ions in as many situations as possible, and then able to treat them as they must be treated. So we're going to use our T-chart that we've used to represent our work. Now again, on the left side of the T-chart, this represents all of my reactants. So everything to the left of the arrow belongs to the left of the T. Everything to the right of the arrow represents everything in the products. Now I'm simply going to, on the left, identify which elements are present. And again, on the right, I'm going to represent in the same order. I'm going to ignore the order that they are up here because, frankly, whatever is on the reactant side must also be on the product side, and I think that it's easier to show my work and check at the end to make certain that it is balanced if I put them in the same order. So the first thing that I'm going to do in the first row is represent the amount of atoms of each element that I have, and in this case, the amount of ions that are present, because we've got our polyatomic ion, and we're going to balance it all together because, as we see, nitrate is on both the left and the right. Now on the right we have 1, 1, and 2. So in order to balance this chemical equation, we need to make certain that we have the same amount of nitrates on the right as we have on the left. Since we have 2 on the right, that means that we must get 2 on the left. Since we cannot change the subscripts, that means that we must change the amount of silver nitrate ions that interact with our zinc. And in order to do so, we're going to change the coefficient to a 2, which means that now, since we didn't change anything here, we're going to end up with 2 silvers, 2 nitrates on the left. We'll end up with 1, 1, and 2 on the right. Now this is not quite balanced because we still need to balance the silvers on the right. So that means when zinc reacts with silver nitrate, we will have 1 zinc atom for every 2 silver nitrate ions, and we will produce 1 zinc nitrate ion and 2 silver atoms. Now, as we can see, it's quick and easy for us to check to make certain that the numbers appear in the same order because I ordered them the same up above. Since I have 1, 2, 2 and 1, 2, 2, that indicates to me that that is a balanced chemical equation. So our first tip is to keep all polyatomic ions together. It would have been much more difficult had we separated them. Next tip is to reduce. As we see in the sample problem below, it's, the same sample problem as the last one. So suppose that as we're working through our problem, for some reason we decided to go to 4 silver nitrates, 2 zincs, 2 zinc nitrates, and 4 silvers. Let's check to see if that's balanced very quickly. So we have zinc, and we've got 2 of them. We have silver, and we have 4 of them. Nitrates, we have 4 of those as well. On the right, we have 2 zincs, 4 silvers, and 2 times 2 is 4 nitrates. So yes, this is balanced. However, it is not correctly balanced. We can reduce. Again, in order to reduce, we need to find the least common denominator between all of these. And I'm sorry, I just realized that I misled you. Not the least common denominator, but instead the greatest common multiple between all of them. And by a greatest common multiple, I mean greatest common factor. So the greatest common factor is simply the largest number that goes into each of these, which in this case is 2. So by reducing this, we are making this the most efficient chemical equation as possible. Since all these can be divided by 2, it is quite all right for us to overshoot when balancing our chemical equations. If we end up with this, that is not the worst thing in the world because we can recognize that we can divide everything by a 2. If maybe we could take a 3 out, then great, that's fine. Sometimes it's easier to overshoot the correct answer to arrive at the correct answer as long as we recognize that we needed to reduce. All right. So those are our first 2 tips and tricks. For our next set of tips and tricks, these are all set for many atom equations. So these are the equations that have quite a few different atoms and are very difficult to balance. So if we encounter a many atom equation, in general, I recommend that you first balance the element in the molecule with the most different atoms. All right. So we're going to take a look at the sample problem below. The sample problem says write the balanced chemical equation to represent the complete combustion of methane gas. Now, methane gas, chemical formula CH4. Since we know that a combustion reaction always, for the most part, has the same reactants and products, we are going to be able to write the equation for this reaction based on just this. So since we know that the hydrocarbon that's being combusted is methane gas, we also know that a combustion reaction, similar to a fire, or oftentimes is a fire, requires oxygen to burn. Most of us know that. So we know that in our reactants, we need oxygen. The result of a combustion gas or a combustion equation between a hydrocarbon and oxygen will always be carbon dioxide and water. All right. So, as mentioned, tip 1, balance the element in the molecule with the most different atoms first. So, it appears that we have 2 options. We can either balance CH4 or methane first, or we can balance, or the C and CH4, or the H and H2O. In this circumstance, I'm going to choose the carbon first. So we'll balance carbons first. In the end, you could choose either of them. But as a hint, if you see a combustion reaction, I recommend balancing carbons first. So we have C, H, and O, C, H, and O. On the left, I have 1 carbon, 4 hydrogens, 2 oxygens. I have 1 carbon. When we get to these oxygens, we notice that they are in 2 separate molecules. However, we want to keep them together. So 1, 2, 3 total in that T chart. Now we're going to balance the carbons first. I see 1 and I see 1. Those are balanced. Check. Good. Next, we're going to balance the hydrogens because those are combined with more different elements. And as we see, we want to balance all other combined elements before we move on to our uncombined elements. So since hydrogen is combined with something else and oxygen is not, I'm going to save oxygen for last. Because at the end, I can change the coefficient in front of oxygen to whatever I need it to be without affecting anything else. So since I have 4 on the left and 2 on the right, we're going to change this to a 2. So we have 1, 4, 2, 1, 4, and we've got 2 plus 2 is 4. And this one is, as we mentioned, the last one that we're going to balance because I need 4, so that means that I can just change the coefficient to a 2 to give us 1, 4, 4, and 1, 4, 4. Now, I'm sure that you're asking, what if it's not this simple? Well, that brings us to our bonus segment